Hello, and thanks for using TickBoom. In this video, I'm coming back to the Year 6 hexagon question that I've taken a look at in a few recent videos. The first video, I worked through an approach that I came up with, and then in the follow-up video, I worked through an approach that another of my Master of Teaching colleagues, V, came up with. In this video, I want to work through another solution that actually I think is the best possible way that you can tackle this question, because it kind of lets you get straight to the answer without having to iteratively fill out a table. If you haven't already, I'd recommend taking a look at the other two approaches that I've already worked through. That way you can get a bit of background to the question. So I'll put some links up for those. But basically, the short story is you've basically got a diagram that I could probably just bring up here from my last approach, where you start off with a hexagon and then you add 3 more hexagons, and then you continue to expand the shape by adding more and more hexagons. And in both approaches, so if I just flick back, the first approach I came up with involved filling out a table based on a pattern that I found to eventually work out the number of unique edges in the 20th expansion of the shape. Then for V's approach, slightly different pattern, but same kind of reality, whereby we've had to fill out a table to eventually get the total number of unique edges. I've called it TN for the 20th expansion. Now what I want to do in this video is share this formula that I've derived that lets you work out the number of unique edges T for any n greater than 1, just using this simple formula. So no need for drawing up hexagons and counting, just straight away you can get the answer. So for example, if I was to think about T20, which is what the question was about, I could just get out my calculator and do 9 times 20 squared minus 9 times 20 plus 1, and we get 3,421, which we can very easily verify is the answer 3421, and that's also the answer that I got to with my approach. So obviously that is a much quicker way to get to the right answer. And so what I'd like to share in this video is just the derivation of this formula. How did I come up with this? Now I should clarify that chances are a Year 6 student wouldn't be able to come up with this formula, because at least one of the techniques I used isn't something that you'd learn until around Year 11 or Year 12 in high school, if you're following the kind of sequence of learning that most students typically follow. So again, the approaches I've already gone through are probably doable for a Year 6 student, but this approach I think is still interesting, because you get to this very simple formula that can give you not only T20, you could do T100, T1000, and you'll still get the answer. So it's a much more generic approach that could let you do higher and higher expansions. So in terms of the derivation, the starting point, what kicked this off is, I'll just write it out, a formula that is along the lines of Tn, so the total unique edges at the nth expansion, is equal to 6 times the number of hexagons and at any expansion, and that's the total number of hexagons, not the new number of hexagons. So again, if you've watched my other videos, you may remember for V's approach, I defined Hn to be the number of new hexagons at each expansion. So I can't really use H, I've already used that. So what I might do is I might just use X to represent the total number of hexagons. So I'll call that Xn minus what I'll call On, which is the outside edges. So for example, on any expansion, if I was just to count the outside edges, how many would there be? That I'm going to call ON. And interestingly, when I was first thinking about this question, I totally misunderstood what the question was requiring. I actually thought we were being asked to work out the outside edges at each expansion. And it wasn't until later that I realized we were actually being asked to count all of the unique edges. But it was just almost a fluke that in me working out the formula for the outside edges, that actually gave the light bulb moment to the other Master of Teaching student who showed this question to me, Yi. He then was able to take what I'd worked out and come up with this formula. So it goes 6 times the number of hexagons minus the outside edges on 2 plus the outside edges. So I'll call that Yi's formula because that's what Yi came up with. And it's from there that I'll then derive this kind of very, very simple formula where you just plug in the n. So basically, I think the first thing you could probably do here is I could clean this up a little because I could say that's the same as 6x to the n minus on on 2 plus 2on on 2. And so I could just bring this all as into one fraction. So we get 6xn minus 1on plus 2on would end up just being 6xn minus 1 plus 2 gives you plus 1. So plus on all on 2. And now what I can do is if I can kind of get a function for xn and on in terms of just n, then we can simplify everything down to here. So I'll just note in terms of our definitions, we've got Tn is the unique edges, the total unique edges. Xn is equal to the total hexagons. And on is the outside edges. And these are all at the nth expansion. So that's what we're dealing with. I'll start with xn. So if we think about how we can get a formula for xn in terms of just n, if I go back to V's approach, actually, you'll see that the total hexagons at any expansion would just be adding up all the prior new hexagons. And so really, we can kind of start by saying the total hexagons is the sum of the new hexagons at each expansion, Hn. And if I just kind of write that out, we can see from the table of my other approach, we get 1 and then 3, and then we get 10, 16, 22, and so on. And from this third expansion onwards, it's always increasing by 6. So we can kind of say it's going to be 1 plus 3, no, say, plus 10 plus 16 plus 22 and so on. And we're going to keep adding up items until we get to the nth item, whatever that happens to be. And this 1 plus 3, the first expansion and second, it's always going to be 1 plus 3. It doesn't really ever change. And then you're going to have however many items remaining, but there'll essentially always be n minus 2 things that we keep adding that kind of starts from 10 and you keep adding 6. And so this is the bit where a Year 6 student probably wouldn't notice this, but actually this part here, we can think of that as an arithmetic progression. And the result in relation to arithmetic progressions that we can use is the fact that the sum of an arithmetic progression is basically I'll just call it the sum of an AP, we could write that, or the result that you'd probably learn once you're in year 11 or 12 is that it's equal to n on 2 times 2a plus n minus 1d, where in this kind of world, n is equal to the number of terms that we're adding up, a is equal to the first term, and d is equal to the kind of, I guess you could call it the difference, the amount by which each term grows constantly. So kind of taking that result, we can actually say, well, here for xn, what we're really going to get is 1 plus 3 is always 4. And then this remaining bit here, well, what that will add up to is we've got n minus 2 items. So wherever we see n, we'll just put n minus 2. So we'll get n minus 2 on 2 times 2 times the first term a. Here our first term is 10. So 2 times 10 is 20. Plus n minus 1. Well, in our case, it would be wherever we see n, we put n minus 2. So it will be n minus 2 minus 1, or n minus 3. Times d, where d is the difference, and for us the difference is always 6, so times 6. So now what we can do is we can think about simplifying that. So that will be 4 plus n minus 2 on 2 times 20 plus, I'll just expand this 6, so 6n minus 18. So what that will be is 4 plus n minus 2 on 2 times 6n, 20 minus 18 is 2, so plus 2. And that I can actually, to help simplify, I'll just factor out a 2 here, so it's times 2 bracket 3n plus 1. And what that means is these 2's will cancel, so we'll get equal to 4 plus n minus 2, 3n plus 1, and I might just expand that. So that will be 4 plus 3n squared plus n, 3n squared plus n, minus 6n minus 2, and bringing all that together, what we will get is we'll have our 3n squared, n minus 6n would be minus 5n, and then 4 minus 2 would be plus 2. So that's basically how we can write xn in terms of just n. The key to it was noticing that we're dealing with an arithmetic progression and you need to have learnt what the sum of an arithmetic progression is. So I might turn over now and we'll take a look at ON. So ON being the outside edges at any expansion, I didn't actually work through this concept in the other two approaches that I've recorded solutions for. And that's because it kind of wasn't required for those. But basically, when I had misunderstood this question and what we were being asked to find, I'd kind of stumbled upon another pattern, and the pattern I noticed is that at any expansion, the outside edges was always going to be equal to 14 plus 12 times n minus 2. So at expansion 20, the number of outside edges would be 14 plus 12 times 20 minus 2 is 18. And that I just noticed through the manual act of drawing up the shape and kind of counting the outside edges manually, and I noticed that they always seem to be growing by 12 after taking account of the first two items which were fixed. And so yeah, this kind of ended up being quite a crucial element to getting to this very simple formula. So if we kind of just simplify this, so that will be 14 plus 12n minus 24. So that's going to end up being 12n, 14 minus 24 would be minus 10. And I'll just factor out the 2 here. So we'll get 2, 6n minus 5. Okay, so now that we've got our xn and our on both in terms of n, we can substitute them into this formula for Tn, and hopefully it simplifies to the result that I talked about at the beginning. So let's just do that. So we can say, therefore, Tn, the total number of edges, unique edges, will be equal to 6 times xn, so 6 times 3n squared minus 5n plus 2. So 3n squared minus 5n plus 2 plus on, so plus 2 times 6n minus 5, and then that's all divided by 2. So all divided by 2. And so right away we can kind of divide out the 2, because these 2's will cancel and this 6 on 2 would become 3. So we'll end up with 3 times 3n squared minus 5n plus 2 plus 6n minus 5. So if now I expand the 3, we'll get 9n squared minus 15n plus 6 plus 6n minus 5. The 9n squared stays. Minus 15n plus 6 becomes minus 9n. And then 6 minus 5 is plus 1. And that is the result that I started with. And it's specifically for n is greater than 1. And hopefully that's clear. I mean, if you put 1 in here, you'd get 9 times 1 minus 9 times 1 is 0, plus 1 is 1. We know that the total number of edges isn't 1. T1 is actually 6. But from T2 onwards, we can use this. So if I kind of just come back to the table in the previous solution, we can just pick some. Like, let's pick 2. So if I did 9 times 2 squared minus 9 times 2 plus 1, 19. Let's pick 10. If I do 9 times 10 squared minus 9 times 10 plus 1, we get 811. Perfect. 17, just one more. 9 times 17 squared minus 9 times 17 plus 1, 2449. Perfect. So there's just 3 simple checks to verify that, at least for what I know, it's giving the right answer. But yeah, I could now, in theory, if I wanted to work out T1 million, I mean, instead of expanding this 1 million times, which I don't think anyone really has a book big enough to bother, instead of having to do that, now I can just plug in 1 million into this formula and have quite a high level of confidence that I'm getting the right answer. So hopefully you found that interesting. I mean, again, I don't think this is an approach or a result that we could realistically expect our Year 6 students taking this test to come up with, because I don't think there's many Year 6 students who have been introduced to arithmetic progressions and this result. You know, I mean, maybe there are some who have worked so far ahead that they have learned this, but for those who haven't, you'd kind of expect them to just kind of do it with a bit of manual work and noticing the patterns. But yeah, hopefully you found that interesting and informative. Yeah, if you did find that explanation helpful, please be sure to give it a like. And if you're someone who wants to keep their finger on the pulse with the kinds of questions that other students are struggling with, please be sure to subscribe to my channel so that you can stay in the loop. All right, tick boom.